Hello, welcome back to another science stream. And today, right now, we are going to discuss cell signaling. So, hello, Zombilos. Yeah, earlier we ended for a little. Oh, the heart rate. Oh yeah, it's going wild. It's okay. That's a normal thing. That's an everyday resting heart rate. It's just excited to discuss cell signaling again. Just um same as how earlier I ended the Golgi apparatus talk and then went to the cell signaling one, and after that I was like I'm hungry. So I have now eaten. So that's an update. Oh, why is the scrolling hidden behind the chat? There you go. Okay. So yes, right now we're gonna do cell. Was it transduction? Okay, transduction. I did the 120 jumping jacks already earlier, so that's the quota. I'm gonna do the next one tomorrow. I think. Yeah, heist. Why you crying? Science, right? Hello, Polize. Very, very good. Like intro. Yes. What happened, Bella? Did you see the new short that was posted? I think you came from there and watched it. Very nice. It is science today. Earlier, it was science as well, and we are now talking about the cell surface. Oh wait, it's signal transduction from the cell surface to the intracellular receptors. So it's again cell. Nope. Signal. Let me just move the mic so it's a bit nearer. Okay, signal transduction. Signal transduction cascades from the cell surface to intracellular receptors. Intracellular. Oh wait, let me check how's the mic, by the way. I don't know if it's working. It's working, right? Oh, yeah, I think it's working. There you go. It's working. All right. So to the intracellular receptors. What does that mean? We start with the extracellular signal molecule. Okay, this will be a big drawing, so bear with me. This will be a Van Gogh level drawing, hopefully. So you have your plasma membrane. This is the plasma. Thank you for checking, Zombilos. This is the plasma membrane of the target cell. And then target cell. And then you have the receptor. Okay, this is the receptor. Squid Game season 3. Oh my gosh. Okay, very keep that up. I didn't watch it yet, but I'm saving that for thank you. I will continue the Feynman technique right now. I'm saving Squid Game season 3. Wait, Squid Game season 3 and maybe the Kpop DH show maybe for a watch along with ever. But yes, that'll be fun, I think. Oh my goodness. Okay, let me just note that down really quickly. Watch part KDH and the nope, not the plasma membrane. It was the who was it? Squid Games S3. That's gonna be exciting. Okay, so you have the receptor and then you have your signaling molecule above there. It will attach. Hi, adios. You have the extracellular signal molecule going to the receptor, and then can't see. Wait, can't see the notes. And then after that, it will go down to the signaling stuff. I think this will work. There you go. You have the intrasignaling stuff. You go down, and this will be your secondary things. And then they just relay it to the cascade. Oh, and then different enzymes after that. Yeah, I think that one works. So you have three classes of, where is it? Three classes of cell surface receptors. All right. Okay, the three classes would be, I'll draw them again. Oh, well, I didn't draw them yet, so I'll draw it here. Okay, three classes. Let's see. There you go. Three classes of cell surface receptors. You have the ion channel, GPCR, and enzyme couple. So it's ion channel, GPCR, and enzyme coupled. Alright, that works. Now for the ion channel, it would be ion channel coupled. Let's see. You have a receptor like this. It looks like this. That's your receptor. Wow, this is beautiful. This is an example, would be the ACH receptor, okay? That one, an ion channel would gate. It gates it. And then you have a ligand that attaches here, and that would allow stuff to go through. Because the ligand binds, the ligand or the signaling molecule would bind, and then the receptor will undergo a conformational change, and then ions like your sodium, potassium, or calcium would then flow through the membrane. And then you have that. Some more examples would be your adrenergic pathway, and all of the other stuff. All right. And then for the GPCR, the G protein coupled receptor. This one looks weird. So it looks like a squiggly thingy with this, and this is your inactive. Oh, this is gonna be a big flow. So I'm gonna draw it later, in a bit. Just remember that this one will be, you have an inactive GPCR. Oh, sticky note. Then you have your G protein over here and an inactive enzyme. So the way it goes would be, okay, first the signal molecule would go here to your GPCR, and then after that this G protein with the alpha, beta, and gamma would be activated, and then the enzyme, what's the flow? Ligand binds, ion change, GPCR activates the G protein and exchanges it and takes the G alpha subunit. G alpha, I said alpha, beta, and gamma, right? The alpha would dissociate from the beta gamma and would then talk to this enzyme. The alpha would talk to that enzyme. And this one is the adenyl cyclase phospholipase C, which triggers stuff like the CAMP and the IP3 DAP. Wow, I need more space here. CAMP and IP3 DAP. So again, GPCR, I'll draw it again. GPCR. Here, so 3 classes earlier. The second class was GPCR. This one is ion channel coupled. And then earlier it was enzyme coupled. Okay? GPCR, G protein coupled receptor. You have the squiggles, right? And then you have the G protein, which has alpha, beta, gamma. And you have an enzyme here. Alright, that's in the membrane area. So first, a ligand binds to the GPCR. And then it will cause a conformational change wherein the alpha, where wherein the alpha, whoa, what happened? Wherein the alpha subunit would detach from those and then would talk to the enzyme. It activates that enzyme. Which enzyme? The adenyl cyclase phospholipase C. And after that, it would then, what's this called? It would then trigger some other stuff like the CAMP and the IP3 tag. Alright, nice. And then with the enzyme coupled receptor, this one is funny. It's very funny. So you have two things. It looks like this. Those would dimerize after your signaling molecule would attach here. They would then dimerize together, and now you have an active catalytic domain. So that's how it goes for the enzyme coupled receptor. So again, the ligand induces dimerization, and the dimerization activates the intrinsic enzymatic activity. Receptor would then autophosphorylate itself, aka just adds its own P, and it activates the cascades like the MAP kinase, like the that's the ERK and etc. pathway. So yeah, that's the mini nutshell for the cell surface receptors. Just the cell surface for now. And then we'll move to, guess what? We'll move to the types of intracellular signaling mechanisms that regulate responses. Hello, George. Welcome back to the stream. It's been a while since I streamed, right? It hasn't been about 1 to 2 hours of a gap. But we are back with a continuation of cell signaling. And right now it would be the types of intracellular mechanisms, cellular signaling mechanisms. Just continuing from earlier, I finished refilling the tank, and I have now eaten, so I am not hungry anymore compared to earlier towards the end of the stream. I was like, I might be hungry. So yeah, finished eating. Now we have phosphorylation. Okay, phosphorylation, what is that? This is when you add phosphate. PO4 3 or 2? Yeah, 3. Right? Let me zoom in by bringing the notebook nearer. Oh yeah, it is 3. PO4 3 minus 2 proteins. You add phosphate to proteins, to amino acid residues like the serine, threonine, and tyrosine. Good question. It was scrambled eggs and rice and ketchup. So simple but filling. Yes. It was a quick meal. Very, very easy to prepare. And serine has an OH. Oh gosh. CHCOOH H3 H2N, and then CH3 CH2 and OH. Good. And then threonine, serine and threonine. Threonine is a weird one. It is H2N. It is COH. CH. Essentially, it's like that. And OH. So CH3, CH2, OH. Tyrosine is a Y. I like tyrosine. It's okay. We will learn to like tyrosine. It's gonna be a friend. It's H3, H2N, and C, this benzene and this OH. Looks quite nice. Whoa, wait, is the OH of tyrosine at the other end? Let me see. tyrosine structure. 1, 2, yeah, it is at the other end. So it's perfect. In my notes, it's at the weird angle. Just wanted to make sure that I was writing the right one. All right. Mini review again. Phosphorylation is adding phosphate to the amino acids of proteins, specifically S, T, Y, and it would be C, H, this one COOH, this one is H2N. I'm just so used to writing H2N plus. This is CH2OH, this is HCCOOH, H2N, CH2, another CH3, and this one has OH. Perfect. And then the tyrosine would be HCCOOH, H2N. This one is gonna be C, benzene, H2OH. Perfect. Good. And then dephosphorylation is just removal of phosphates. So who does phosphorylation? Kinases. Who does the dephosphorylation? Phosphatase. So it's more of an on and off thing. Oh, I should change my hat. Exclamation hat. Nice one. Okay. So G protein. Oh, the next one is just G protein activation, and deactivation. This one would involve the trimeric G proteins, alpha, beta, gamma, like earlier, associating with the GPCR, the G protein coupled receptors, wherein how would you activate it? Earlier I mentioned the ligand binds to GPCR. GPCR talks to the alpha subunit of the G protein, which has the alpha, beta, and gamma. The alpha subunit would then activate your adenylyl cyclase or phospholipase C. And then to deactivate it, it's just a normal GTPase activity, like hydrolyzing the GTP to GTP. Nice! And G alpha would then reassociate with your beta and gamma. Oh, and for monomeric G TPase activation, it's very similar to the G proteins, but it involves the smaller GTPases like the RAS, Rho, and RAB. What is RAS? RAS is a cell proliferation via the MAP kinase cascade. Okay, I think this one needs to be written. It looks like a table. RAS, Rho, and RAB. Okay, so RAS is cell proliferation via MAP kinase. Rho is cytoskeletal dynamics, and RAB is vesicle trafficking. All right, RAS, Rho, and RAB. Okay, again, RAS is cell proliferation, Rho is cytoskeletal dynamic, and RAB would be vesicle trafficking. Next is your, what's this called? This one. Next is the secondary messengers. Secondary messenger. Now, how does this work? Good question. So you have a small molecule, right? Small molecule, which would increase and amplify the signals and relay them. So some common ones would be your CAMP, like the cyclic AMP. The second one is your calcium. Oh, for camp, by the way, it is produced by the adenylyl cyclase and then activates the PKA. A drawing will be made pretty soon. Pretty soon. But yeah, this one is made by adenylyl cyclase, and activates the PKA. Calcium would be released from the ER via IP3 DAG, via IP3, and activates the calmodulin and all of that. For number 3, you have the DAG, diacylglycerol, which will work with calcium and the PKC. So that's an important thing. Again. 3 small molecules will be CAMP, CAMP, calcium, and DAG. CAMP is made by the adenylyl cyclase, and then goes through the. Oh, hello! Welcome to the night in training, Matthew. Yeah, for the CAMP, it's made by the adenylyl cyclase, and then it activates the PKA, and then you have your calcium, which is from the ER via the IP3, and then DAG is calcium and works with the PKC, protein kinase C. Sticky note. One moment. I don't remember this. Okay. I mentioned a couple of things earlier about the G protein coupled receptors, right? For the G protein coupled receptors, erase. G protein coupled receptors. This is the GPCR, and you have the trimeric GT. Oh, the handwriting. Again, you have the G protein coupled receptors and trimeric GTP binding proteins. What is that? Okay, I'm gonna try and draw it. You have your membrane, plasma membrane. You have the GPCR. This is where the ligand goes, and this is where, this is the cytosol. This is the extracellular space. And then this one is the G protein interacting domain. Now, at the other side, you have something that looks like this. Just floating. You have the alpha subunit of the G protein, aka this is the RAS domain. And then you have the GDP here. And then you have the beta. And then you have the gamma over there. Okay? Now the if GDP is bound to the alpha subunit, it is inactive. But when GPCR is activated by your ligand here, then it would act as a JEF. Again, it would act as a JEF, a guanidine nucleotide exchange factor, which would then lead to this changing into GTP. And after that happens, the alpha subunit will then activate another thing that's over here at the right side, but it's something called your adenylyl cyclase. Alright? So GTP causes G alpha to dissociate from the beta and gamma. The G alpha and beta and gamma would then activate the different receptors. Yeah, that's true. As for which receptors they will activate, One moment. It would be, okay, the G alpha and beta and gamma would activate different stuff, right? So if it's the G alpha stimulatory, it would increase the adenylyl cyclase, thus increasing CAMP and increasing pKa. But if it's the inhibitory, then of course all of those would go lower. If it's the G alpha Q, it would activate phospholipase C, the beta version, which would then do IP3 and DAG, and then greater calcium, and then activating PKC. So again, that's the one of the difference between them. If it's G, so after the G alpha dissociates, it depends what type of G alpha it is. If it's G alpha S, if it's the S or Q. If it's G alpha S, it would go through the adenylyl cyclase, then the CAMP and the pKa route. But if it's G alpha Q, then it would be phospholipase C and IP3 DAG, calcium, PKC. That's the simplest way we can explain what those are or what those do. So to prevent like overstimulation, the GPCRs actually undergo desensitization. Through what? Through phosphorylation by GPCR kinases and then arrestin binding. They also go through arrestin sequestration, where they get internalized via endocytosis, or they just get degraded, just overall destroyed, or back to the plasma membrane. So yeah, just so they don't get overwhelmed. Okay. So for the next one is just the secondary messengers. Secondary messengers. Okay, here you go. Secondary messengers. Messenger. These are small intracellular molecules found that are formed or released for activation in response to the signal. So the biggest examples would be the CAMP, like cyclic AMP, cyclic GMP, and inositol 1,4,5 triphosphate. Guess who is that? That is the IP3. And then you have your diacyl glycerol, the DAG. And then you have calcium. And lastly, nitric oxide, the NOx. Nitric oxide. Nope. I'll write it properly. Erase. There you go. Nitric oxide. Nitric oxide. Okay, perfect. So, nitric oxide. Secondary messengers are rapid. So, for example, just 20 seconds, the neuron could respond to it. So, an example would be serotonin, okay? Serotonin. It would bind to GPCR at the neuronal membrane. GPCR activates GS, and since it's S, it goes to the adenylyl cyclase route. Adenylyl cyclase converts ATP to CAMP, okay? And then CAMP diffuses within the cytoplasm, and then downstream would be to activate pKa. So I will try to draw this one a little bit. This is a review. So again, we have the GPCR over here. serotonin is here at the neuronal membrane. Now GPCR activates the GS, aka you have the G alpha, G beta, G gamma, and the gammas like that. And then this G alpha is an S type, so it now activates adenylyl cyclase, which converts the ATP to GTP. Note the way it does that is ATP looks like this, right? Kind of like that. OH, OH. This one is O. This one P, O, P, and then O. At the phosphates, kind of like that. And stuff like that. Basta 3. And then this one's adenine. So it's like this. 5. Yes. N. Good. And then you have like this. N. NH2. Adenylyl cyclase with a GS stimulates it, but GI inhibits it. And now you have CAMP. What is CAMP? So, this one's weird. You have this part again, still the OH, your adenine, but then you have the O, and then you have the O. This forms a box, and you have an O here, and that oxygen will have that. So that's CAMP. That is CAMP. And then the CAMP would just activate the pKa. Later on, I will just draw the full thing after it. But yes, I think that we could go here. This one is just a big camp actually. Yeah, but I think we could pause there because I want to make sure we have enough like time for the next few ones. All right. Thank you for coming by to the stream. Ta-ta.